Okay everyone, after reviewing day one, or at least reviewing it a little bit in my office, I noticed that it's still getting a little loud, a little crackly, a little reverberation in the recording. So I'll try super hard to keep my voice right here, which is basically a whisper, believe it or not. And I've also made one more adjustment to the microphone in the room, so maybe this is a little less staticky and a little nicer to your ears. I apologize. At least it's not making that horrible reverberation that was happening whenever I first started. Okay, so here we go. Integer arithmetic and polynomial operations. Now, if you know what polynomials are, that's usually like a quadratic function is a polynomial, right? It's got x squared plus 5x minus 7 or something like that, where poly means multiple and nomial means names or multiple terms, basically in this case. Okay, so whenever I have like x squared plus 5x minus 7, I've got multiple terms in there, and we do operations with those. So normally the polynomial operations is the same as the integer arithmetic. It's just that this only has whole numbers, integers, right? Adding, subtracting, multiplying, and dividing. That's what arithmetic means, right? Those are all my operations. And polynomial is the same thing, but with the polynomial operations, it means add, subtract, multiply, divide with variables thrown in there, okay? So to do this, we're going to use Algeblocks, and we're going to use a couple of the basic mats and the quadrant mat, okay? A couple of the mats for the Algeblocks, so I'll show you those as we go along. So as I'm thinking about it, I think, okay, we did addition last time. I spent a lot of time really talking about the difference between the two kinds of blocks, algebra tiles versus Algeblocks. So I'm not going to spend as much time with that this time, but we're going to do this instead. I'm going to just keep a list of the problems we're working here. Use a mat and Algeblocks to model. Okay, and I'm going to tell you right off the bat that some of this stuff I will be doing is a little more advanced. I'll try to stick with a lot of x and x squared stuff so that you can do it if you have your algebra tiles at home, but I am doing Algeblocks. So if I go into x cubed, or if I get some y stuff in here, or if I get the xy pieces in here, it's because I know you need to be able to see those and understand those, and so I'm going to still show you those things, but and you'll know that you can model upper level stuff, but I'll try to keep it mostly to the x's, because a lot of what we do in all the way through, like Algebra 1 or Algebra 2, is x and x squared stuff, right? So normally your algebra tiles will be sufficient. You can model along with me, and that would be excellent, okay? So I'm going to just kind of focus in on the polynomial operations and assume that if you can do these, you can do integer stuff. So for instance, you guys all know, we did the last time, I think, positive 8 plus a negative 5, right? Okay. So we said, all right, we're going to add onto the mat a positive 8, and we're going to add onto the mat a negative 5. Well, I'll show you subtraction in a minute. But whenever I do that, it means I have to have the mat. We have this basic mat. Hopefully you have one at home, or you can just make it on your piece of paper. You could always draw, like, here's my piece of paper, and put a positive over here and a negative over there. It doesn't have to be colored or whatever. So that's sufficient. That's the basic mat, right? Okay, because it's the same thing. Positive over there, negative over there. Okay, so we're going to use our basic mat, and we're going to do positive 8 plus a negative 5. And we did that, I think, last time, but I just want to make sure we're still on the same page. Okay, so there's a positive, oh, I actually put them on backwards, didn't I? I'm sorry. Positive 8 and a negative 5. Yeah, positive 8 and a negative 5. Okay, so So there's the positive 8 and the negative 5, and what we need to do is make our 0 pairs. So we're going to put those together. So if you remember, you pick one on the positive side and one on the negative side, and we're going to match those guys up, right? And I like to normally I'll kind of line them up along the line here so that we can see what's matching and why I'm about to get rid of these things. And it's because their signs basically, a lot of people say cancel each other out, but I'm going to say zero each other out because that's the 0 pair, right? 0 pair, 0 pair, 0 pair, 0 pair, 0 pair. There are 5 0 pairs here, right? And so all of those added out to be 0. They'll go away. And what do I have left? I have a positive 3, right? Okay, so it's not enough. It's not enough that you know that that's a positive 3. We're all adults here. I expect that you know that that's a positive 3, right? I'm going to be not happy with you if you don't know that that's a positive 3 when I add those out. The process, though, of making the 0 pairs, the process of demonstrating that you know what it looks like, the process of pulling that stuff off and then showing me what's left over, that's what's got to go in your video whenever we get to right at Thanksgiving time and you're starting to put together your test number 3, right? So that's what you've got to be able to demonstrate back to me. So you really need to take some time in the next few weeks while we're working with the algebra tiles and the Algeblocks. You need to take time and actually model these with me. It's not enough to just watch me do it, okay? I know that you understand. Oh, I get that. Okay, I'm glad that you get that positive 8 and negative 5 is a positive 3. But if you can't sit here and actually physically, without watching me do it, you come together and put all this in there and go, okay, think through, how am I going to do this? I know that those are 0 pairs. I'm going to pull them all off. I know what that process is. If you can't do it without watching me do it, then that means when it comes test time, you're going to struggle, okay? Because your test, as I've said many times now, is going to be a video where you demonstrate to me that you can do this, okay? All right, so what I started to say a minute ago was this operation is the same exact operation as doing this. We already know. Positive 8x plus a negative 5x, I'd better get positive 3x. Yeah, it needs to be exactly the same as what's above, except for instead of the unit guy, I'm now using what? Which piece? Think to yourself. Which piece is the x? Yeah. The yellow long, right? So I need negative 5 of those, and I need positive 8 of those. Again, with the Algeblocks, we don't have the red pieces, right? So I don't have a piece for each piece that tells me that's negative. So that's kind of one of the drawbacks of the Algeblocks is it doesn't have the built-in negative, so I really need the mats to be able to do Algeblocks. Okay, so I've got that, and we're going to do it. Okay, so the process is the same. I put on the positive 8x, I put on the negative 5x, and then what? What did we do last time? We made our 0 pairs, right? And that's one of the hard, it's like an easy concept, but it's hard to kind of make ourselves do 0 pairs. So think to yourself, what are we doing? If you were combining like terms, is what a lot of people would say, right? Okay, 8x plus negative 5x, I combine like terms. How in the world do you explain to a kid that positive 8x plus negative 5x is a positive 3 whenever they combine like terms? You have to be able to explain why that means combine like terms. What the heck is going on? Why isn't that, for instance, 13x? Because if I'm just combining, that's 8 and 5, right? Okay. So I need to be able to explain to them why I actually get a smaller number. Why is my answer a positive? Why is my answer a 3? So the answer there is, the reason why that happens is 0 pairs. Okay, I pick a positive x and a negative x, and I match them up. That's what the pairing process is. Match them together. If you run out of space, stack them on top of each other, whatever you have to do. But I've got 5 of them that all pair up. A positive x and a negative x, those go away, right? I get a 0. 0, 0, 0, 0, 0. All of those are zeros. All of that goes away. What's left over? Positive 3x. Okay. So also on your video, you should make sure that whatever you're showing me as your answer here matches up with what my answer is here. So hopefully, if I had left that as a negative 3x, at the end where I have this as my answer, I would go, wait a minute, there's a problem. What's going on? Well, the problem was I didn't take the sign of the bigger number earlier, right? I need to take the sign of the bigger number. So all of that plays in so that I can do things like this. Okay, so real quickly, I want you to do this next problem. You need to model it. You need to model it and show me what your answer is. So negative 5x plus 2x. Pause the video if you have to, if you need to. You should really do some of this yourself and make sure you know what it looks like when you're doing it, not just when I'm doing it. So what's that going to be? Negative 5x plus 2x. What's going to happen? 0 pair, right? There's a plus and a negative in each one of those. Those go away, and what are we left with? Negative 3x, right? Okay. So, I know I did that kind of fast. I'm going to work through some problems. I want you to see it. Okay, so now what about the x squares, guys? I want you to work some of these. So this is going to be an x squared problem. You should be able to do these with Algeblocks. So how about negative 4x plus negative 4x? Can you do that? You might not have enough algebra tiles for that, but I think you do. Okay, negative 4x plus negative 4x. Sorry guys, I know that was probably loud in the thing. So I'm adding on to the mat 4, and then I'm adding on to the mat 4 more. So I've got what? I said x. I said I was going to do x squares. Sorry. Negative 4x squared plus negative 4x squared. I'm like, why doesn't that match up? So negative 4x squared I put on, negative 4x squared I put on. Altogether that's negative 8x squared, right? Okay. So that's kind of the adding part. Something you need to know about subtracting. If I'm going to do subtracting on one of these mats, and it's honestly the subtraction operation, then what I do is again, when I've been adding, I've been putting things on the mat, right? Whenever I subtract, I'm going to take things off the mat. So instead of putting on, I'm going to take things off the mat, okay? So let's do an actual subtraction problem. We haven't done any of those. All of mine have been adding on, right? So here's what's happening here. Let's do just a plain old integer problem. So how about 7 minus 3? Okay. Notice that it's a minus. It's not plus or negative 3. So I'm not putting on both sides of the thing. I'm going to actually read this from the left to the right. I need to put on 7, because that's a positive 7, right? Put on 7. Okay. And then I need to minus or take away 3. So I'm going to take away 3. What's left over? 4. Well, we knew that, right? Okay, so again, put on the 7, take away the 3. What's left over? So when I see this minus thing in the middle, I'm actually going to take it off the mat. So those were positives. So let's try something different. How about negative 7 and I want to minus 3? Okay, just for our purposes as adults, we know that should be negative 10, right? okay, whenever I'm finished. So negative 7 minus 3. 1, 2, 3, 4, 5, 6, 7. Well, what it's literally telling me to do is take off 3. Take off 3. I don't have anything over here to take off, right? So this is a weird process for us, and it actually kind of helps kids sometimes to understand why is that negative and a negative. Whenever I'm doing this, we said we're going to get negative 10. We know that as adults. How in the heck am I going to get negative 10 out of this? I need to take off 3. But you're telling me that it's going to end up with negative 10. I'm going to have more over here on the negative side. And the answer is 0 pairs. Okay? So if I want to take off 3, and they're not over here on the positive side, then I need to put them on there, right? Put 3 on. Can I just do that? No, I can't just do that. If I just do that, then I'm in trouble, right? So if I just want to do that, then I just change the way this whole thing looks, all right? That's negative 7 plus 3. That's not what I'm asking. Okay, so, and I've changed the entire feel of this. I put an extra 3 on. I can't put on an extra 3 in an expression, we're not in an equation here, unless I put on a negative 3, right? Is that okay? Let's think about it. Let's line them up. What I'm saying is I'm going to add 3 0 pairs. Well, if I'm adding zeros, does that change the way things look? And I'll show you the arithmetic for it in a second. No, it's not going to change the way it looks, right? So if I'm adding zeros, this is what this arithmetic looks like. We had a negative 7. We couldn't do minus 3, so we did a plus 3 and a negative 3. That's a 0, right? So I haven't changed anything yet. I'm just adding on so that I have enough stuff that I can pull off. So I put in a plus 3 and I put in a negative 3. But hey, that's a 0. I'm not really changing anything value-wise. It just looks different. And why do I want it to look different? Well, I want it to look different because, let's see here. Now, whenever I say, okay, what I've really got here is negative 10 plus 3, okay? Negative 10 plus 3 is negative 7, right? So again, I haven't changed the value. I've still got a negative 7 sitting there. Okay, I'm just changing the way it looks. Now I can go in and take away or minus those 3. Okay, take away or minus those 3. So this is just a 0. That doesn't change the value of anything. But what it does is it puts onto my paper some positives that I can take away. So whenever you see subtract, you should be thinking take away. And now, by the way, what the heck happened here? Yeah, that's how I get extra negatives over there, right? Is now I have a total of negative 10 over there. So that's what happened. So in the arithmetic end of things, we see, okay, well, I had negative 7 minus 3, or you can think I added on this negative 3, and I got rid of that plus 3 and the minus 3, right? Because I added the 3, I subtracted the 3. So that's why I've got negative 7 and a negative 3 gives me negative 10. Okay. Uh-oh. I think the thing just squealed. I'm sorry, guys. All right. So we've got an answer in there. That's awesome. Okay. How about this? How about an easier one? Let's do negative 5 minus negative 2. Think hard about that one. Negative 5 minus negative 2. Now we know in our adult minds that those negatives will cancel out, right? So that's kind of like a negative 5 plus a 2. So that should be negative 3, right? Negative 5 minus negative 2. So we know where we're headed, but let's see how this is going to look. That's my negative 5. and I want to minus or take away negative 2. So there's my negative 5, take away negative 2. Oh, that's way easier than the last problem we did, right? Because we didn't have to zero pair anything. So let's think about it again. Negative 5, take away negative 2. That's way easier than that problem we just had. Okay? No worries there. Negative 3. But all too often people go, oh, we want to switch that, right? Okay, so think about it in your head. That's equivalent to a negative 3 because, let's think about that. If we did that process right there instead, that would be negative 5 plus 2, and then we would do our zero pairs, and we have a negative 3, right? So that's why those are equivalent processes. Minus a negative 2 is equivalent to a positive 2. Those are similar processes, but they look different on the mat, right? So if you're not sure about that, go back. This is equivalent, but very different processes. One had zero pairs in it, and one didn't, right? So on your test in a few weeks, I'm going to be very, very picky, because if I give you an actual honest-to-goodness subtraction operation, I expect that you can actually tell me that means you're taking away from the board and you'll pull things off of there. Okay? So remember that as you work your way through things. Let's do one more kind of hard one. How about, let's do 10 minus negative 4. 10 minus negative 4. Okay, so again, thinking to ourselves as adults, we know this is going to be equivalent to 10 plus 4, which should be a 14, right? Positive. So we know where we're headed. Of course, kids don't know where we're headed, so we need to be able to explain this very clearly to them. And that's going to be a huge part of your test in a few weeks. I know I've said that like 50 times already, test, test, test. So it's going to be a huge part of that test is that you're going to need to demonstrate like you would to a child. So this means you can't go, oh, Dr. Webster knows what I mean. She's got to understand this. I'm not going to do anything, right? I'm just going to say, oh, you know, do this. No, it's not enough. You've got to be able to explain it as if you were talking to a child what your process is here. So be sure to show all the little stuff. You can't just skip steps. Okay, we got 10. We want to do minus negative 4. Again, minus means take away, right? I want to take off the mat a negative 4. There's a problem here. There's not any negatives. Okay, I can't take them off if they're not there. Okay, so I've got my 10 going on here. They're positive, but I can't take off my negative 4. So what we're going to have to do is we're going to have to play with this a little bit and make it so that I've got a negative 4 over there. Well, I want to put in negative 4 so that the operation is take those off, right? Before I can do that, though, I got to make sure everything's equaled out here. So this is supposed to be 10 take away negative 4, but I just added negative 4 on. I can't do that, right? It changes what's going on in my problem. I can only do that if I do it on both sides. So you can almost think of this basic math like it was an equation or a balance, because you can't do something to the positive like add or subtract, add on a positive whatever, subtract off whatever, unless that's an actual operation. If it's the actual operation, fine. But if I add a negative 4 here, I need to add the positive 4 or else I'm changing the value of my problem. Okay, so let me show you what that means mathematically. Okay, I just did 10. Oh, let me scoot a little bit. All those cheesy guys are in my way. 10, and I added on a negative 4, and I added on a positive 4, and then I've still got to do this operation, right? I haven't done that operation right there. All I did was right in here, I added on the negative 4 and the positive 4, and what that tells me is I'm really adding a 0. Minus 4, positive 4, that's a 0. So even though it looks a lot different now, let me get this back up there, sorry. It looks different because I've got my 10 and I've got the -4 and the +4. What's really going on is I've got a 0 pair in there now, right? Okay, so I haven't done the operation take off -4, right? I'm about to do the operation take off -4. So I haven't done at the very end there, right? Take off -4. I'm going to do it now. Take off -4. I'm going to pick them up and take them away. And whatever's left over, that's my answer, okay? Now, we know that we have added 4 there, right? Okay, so take off the -4. In order to take off the -4, first I have to use my 0 pairs concept, and then I have something to take off. So this guy is equal to 14, okay? That guy was equal to 14. Now, a lot of people try to tell me, wait a minute, Dr. Webster, I know this is equivalent to 10 plus 4. That gives me 14 also. And you are absolutely correct. The difference being that what you're telling me if you do 10 plus 4 is you're saying, hey, here's 10, and I'm going to add to it or put on 4 more. Okay? So that's what 10 plus 4 means. You've got a group of 10, and then you add to it a group of 4. Put on. 10 plus means put on, or add to the mat, 4. That is nowhere near the process that we just did, right? To subtract the -4. We had to make our 0 pairs, and once we had that and everything was okay, then I take off the -4. So one of the things whenever I'm subtracting the negative, that involves making 0 pairs and taking off something, but this, if I just did plus 4, is just adding on, right? So keep that in mind. That's kind of the difference here, okay? This one is make 0 pairs and take off. That's important, take off -4, that's what's going on there, which is a different process from add onto the mat +4. And I guarantee you, if you do this backwards on the video exam, you're gonna lose points because I'm making a huge deal out of it for a reason. And the reason being that we need to see, while these give me the same answer, the process is very different, right? Okay, now I know as adults, a lot of times we just make those positive and go on, okay? But for showing it to the kids for demonstration purposes, you gotta know why. Why are those equivalent? Why am I getting the same answer? And the point is that one of them involves 0 pairs, okay? All right, so one more problem that deals with this, but we're going to throw in the variables. So the subtraction with the variables, I haven't done any of those. So everybody try on your own. Let's do -4x minus 3x, okay? And again, as adults, we know that should give me a -7x, right? But -4x minus 3x, meaning take off, minus, that's a subtraction, that's an operation. Take off 3x, positive 3x. Can I do it? Not the way it looks right now, right? Not the way it looks right now. -4 off 4x, take off 3x. Well, I don't have positive 3x to take off. So I need to put those on so that I can do this. But in order to put anything on, unless it's an addition operation that says put on, I'm going to have to make 0 pairs. You got to make this happen. You got to do the 0 pairs. So we put on 0 pairs. Now, I didn't do anything weird yet, Okay, I haven't done the actual operation. I've got this going on, plus a 3x, plus a negative 3x. That's the 0, right? 0 pair. I added a step whenever I did this, basically, right? So I've added this step so that I can now have something on the positive side. So now I can do this operation, which is minus 3x, or take off 3x. And whenever I did that, what happened? Yep, now I've got negative 7x. Everybody agree? Minus 7x. Negative 7x, I should say. Okay, so we knew that that was going to be negative 7x, which is awesome. We got the right answer. We like it when that happens, right? Okay. Real quickly, I want to go ahead and show you the other mat. So, and realize that all of that add and subtract stuff would work the same if I was doing x squares, x cubes, whatever I was doing. So when you see some polynomial equations or expressions on your homework, you're not freaking out on me and going, oh my gosh, I don't know what to do with that, because they're still the same, even if it's an x squared or an x cubed or a y squared or whatever. Okay, so here we go. This guy right here is called the Algeblocks Quadrant mat. Clearly it says that. You can see that it looks kind of like if we were graphing something. Okay, if I was graphing something and I had a quadrant, 4 quadrants, it would be first quadrant, second quadrant, third quadrant, fourth quadrant, right? If we were doing a regular old algebra thing, graphing an equation, right? Okay, so we're going to kind of talk about first quadrant, second quadrant, third quadrant, fourth quadrant as if we were in an algebra class, but it's going to be a little bit different because, see, whenever I look here, it's got, again, the mat is telling me that's a negative. Anything that goes in this quadrant, I know it's negative. Because with the Algeblocks, I don't have the red pieces, right? So I have to tell you, okay, it's negative by putting it there. Positives here, negatives here. Now, if you've had a trig class, you know, or even if you haven't had a trig class, let's think about this. In the first quadrant, both my x and my y are positive, right? Okay. So what we're going to see is this quadrant mat is used whenever I'm multiplying and dividing, or factoring, or other stuff like that. But basically, it boils down to multiply and divide. Okay. So if x and y are both positive, then any multiplication of x and y makes this positive, okay? If x is positive and y is negative, like is what happens whenever I'm in quadrant 2, then a positive times a negative is a negative. What's going on in quadrant 3? X is negative, right? Y is negative. You see my axes here? X-axis, y-axis. Okay, so if x is negative and y is negative, then I multiply those together, what the heck happens? Negative times a negative is a positive, right? Okay, so I start seeing those processes in place, those little rules we tell kids, right? A positive times a negative is a negative. You can see that in the mat here. Okay, so on these axes, what we're going to do is we're going to put any problem that we're working out in our multiplication and division, we're going to put it on the axis. And in Algeblocks, they come with yet another little lovely piece that looks like this. And you can tell if you have the big quadrant mat like I do, what? The factor track, that's what this plastic piece is called. That's where my factors are going to be stored. The factor track actually sits right on top of what we know is the x and the y axis. So let's think about this. Let's just do some units. And I tend to just kind of let them lean while they're in the track. Some people are very particular and want them to stand up and down. So if you want them to stand up and down, that is 4 units, right? And I see that this one has a glare, so I'm sorry that my factor track is glaring at you. But if I do 4 units times 3 units here, then we're going to use the fact that we know that the area of a rectangle is length times width, and here I've got length times width, right? And we're going to figure out what rectangle can I create who has a length of 4 and a width of 12. Or you can call it height or whatever you want to call it. Well, it would be one that lines up here, right? They've got to line up. Okay, so it would need a width of 4 and a height of 3. I'm not quite there yet, right? I don't have my rectangle doesn't meet up with all of this, but now I've got 4 wide and 3 tall, right? So what rectangle is that in there? And I usually tell people, pull off the factor track because you don't want to count the pieces that are in the factor track, right? The pieces that are in the factor track are the problem, 4 times 3 in this case, right? 4 times 3 equals 12, okay? And you can tell it because what? You've probably seen this in Math 350, 351. Yeah, I now have a lovely area model, and it's a rectangle that is 4 units wide by 3 units tall, right? Okay, so that's kind of the idea that goes on behind multiplication here. We're making rectangles because we're going to just use over and over that idea of length times width equals area, and that will tell me how big my rectangle is. Okay, using the same problem, oops, just flip one of those over. What if it was what if the x was negative 4 and the y was positive 3? What do we think about that? Well, it's still 4 by 3, the rectangle, right? So it's still 12 units, but now see how I flipped it around? I said the x was negative, the y is positive. That pushed me over into quadrant 2, where x's are negative and y's are positive. And now I can see, okay, they're 12, but they're negative, right? Okay, and then I could just keep on doing this around the entire thing if I wanted to, just shifting things around. What if it was a negative 3 on the x and a negative 4 on the y? Still a negative 12, but now a negative times a negative is a positive 12, right? And then same kind of thing over here. I just need to make sure that my rectangle actually adds up, lines up on the x's and the y's. And now I've got a positive x and a negative y, so I'm in a negative quadrant, and it's a negative 12. Okay. The other thing that I will kind of stress as we go along and do some of these problems is that also please notice that on each of these, where these things are, the breaks on the factor track line up with where the breaks are inside of here. Meaning if this is a unit, then I only want something 1 unit wide. Okay? What do I mean by that? Let me show you one where they're not all units. Okay. So here we go. We need a fresh sheet of paper so we can get some fresh problems up here. Sorry. What if my problem was, instead of 3 times 4, what if it was 3x times 4x? Okay. Well, as adults, again, we know that that's going to be 12, what? 12, is it 12 x's? No, it's x times x is x squared, right? 12x squared. So what the heck would that look like in my factor track? Okay, so this is what I mean by we got to make sure things line up whenever we do this. Alright, so 3 times 4, and it doesn't matter which one acts as the x value on the x-axis here, and which one acts on the y value. As long as they're both positive, I just stick one on each one. Okay, 3x times 4x, right? There we go. Okay, so 3x across here, 4x going up. Okay. Would I, for instance, use this xy guy? Well, no, I don't want him because, first of all, we know x times x is x squared, right? I need this guy. Okay, and second of all, look how these things don't line up, right? It should be breaking at exactly the same point in order for this x times this x to line up. But it's not, because that xy guy is way too tall, right? So don't stick him in there. He doesn't fit, okay? That's what I'm going to be meaning by they need to line up on the breaks. So on the width times the height here, or the length times the width, however you want to think about it, things need to break at the same spot. The x times the x is the x squared, right? Okay, so whenever I think about this, this is a bunch of x squares going in here. In fact, we know how many it is because we already did this multiplication problem. We just happen to be, now we're adding the piece that we need, right? Oh, I might run out of x squares. I'm sorry, guys. So the piece that we need here is the x squared. Okay. There's one more. I got it. I can make it. Yay. I thought I could do 12. Okay, so the piece that I need is an x squared piece, but I know I need 12 of them because 3 times 4 is 12. The trick is just figuring out where everything breaks. Okay? So 3x times 4x is 12x squared. And there is the physical proof for how that works. Okay? Well, what if it was, sorry, 2x times y. Now this is something you can't do with your algebra tiles, right? Because I'm now bringing an x and a y together. So what if it was 2x times y? This one's the one where I need a piece that's an x wide and a y tall, right? And by the way, I don't want to put him like that, right? If I put him like that, things aren't lining up. So if I know it's an x, y, perfect, but I still need to line him up so that he ends appropriately where the other pieces that were being multiplied together end. So what is 2x times y? Yeah, I can see it, right? It's 2xy's. Okay, so this is the problem on my factor track that we did. 2x times y, right? That's what I worked. 2x times y, and what we saw was the answer is 2 of these xy guys, right? That's what lines up. Okay. So that equals 2 xy's. All right, we got it. Yay. Okay, so I wonder if that's the problem. Maybe we'll see if things change right now. I hope that I fixed our issue, guys. Sorry. Okay, so real quickly, we want to kind of work through some more of this kind of stuff. What if my problem wasn't quite x's and y's? What if it was something like this? X plus 3 times, let's do 2x plus 1. X times 3, x plus 3 times 2x plus 1. What would that look like in the track before I move over to the quadrant mat? I'd have an x plus 3, right? 1, 2, 3. And then I'd have a 2x plus 1. Everybody got that? X plus 3 times 2x plus 1. So that's how I would look and model this guy to begin with. Okay? And then we know where we're going, but to prove to children where we're headed, I need to say, okay, I need to line things up. So what goes here? What's an x times an x? X squared. Look at that, it lines up. What's an x times an x? Still an x squared. Okay, now this one's weird for us. What is 1 unit wide and x units long? Or x units tall? Well, that's an x, right? And anytime I see that 1 down there and an x going that way, I know I need literally 1x. 1 times x is 1x there, right? So I need an x there. I need 2 more to line up with this guy. And I need 2 more to line up with this guy. So now I have everything breaking in the right spots and lining up on my, what I consider the x-axis here, right? But what about going up here on the y's? I still have this plus 1, right? So I need to put something in there that fits. Well, what is 1 unit tall and x units wide? What lines up? The x guy, right? Now be careful, because whenever I get over here and I want to fill in these little pieces here, that's really 1 unit wide, because that's how wide those x's were, and 1 unit tall. So what's a 1 by 1 square? 1 times 1 is just 1, right? So the unit fits in there, and the unit fits there, and the unit fits there. And I'm not finished until I have a rectangle built. So let me pull my factor track off. Is that a rectangle? Yeah, it's a rectangle. So it's a big rectangle. It's got a lot of stuff going on in there, but I can see everything lines up on all 4 sides. It's a rectangle. I just need to know what the heck's going on. Okay, well, that was 2x squared. These are x's, 1, 2, 3, 4, 5, 6, 7 of them. And there's 3 little 1 guys, right? So my answer is 2x squared plus 7x plus 3. Let's see what the heck's going on with that. So let me put that up there. 2x squared plus 7x plus 3. Okay, let's think about that. If we were to actually work that problem out up there as adults, we would say x times 2x, you would do your little distribution thing, right? X times 2x, that's 2x squared, right? And then x times 1, what's that? Plus 1x, I'll come back to that. And then 3 times 2x, what's that? Plus 6x, right? So we would combine those like terms and we'll get the 7. So we're good, 7x. And then your last step would be 3 times 1, right? Or 3 units times 1 units. And that would be your 3 there, and you're good. So the weirdness is, what the heck's happening here in the middle? 1x plus 6x. And does our picture demonstrate that? And if you've done some of this in the 350 classes, you should know this is called partial products, right? So here I go. Let me split it a tiny bit and let's see it. Okay. This represents the x times the 2x. That's that partial product, 2x squared. This little piece here represents 2x's here times 3 here, which is 6x's, right? So that's that little piece here. Oh, we had that, right? I wrote it up here, 6x. Okay, this guy up here represents this 1x times that 1, which is just 1x. There we go. And then these little 3 guys here represent 3 times 1, which was the last step of my distribution, or if you call it FOIL, that's fine. Okay, that's the last step. 3 times 1 is just a 3. Okay, and when I put them all together, it makes a very nice compact rectangle for me, where I can see all the partial products in there if I need to, but I can also see the entire rectangle and what my answer is. Okay. So real quickly, what if I wanted to do, I'll do a fairly easy one here, just in the name of time. What if I had asked you guys to do, let's do x minus 3 times x minus 4. How in the world am I going to even demonstrate that? On one of my axes, I need x minus 3. Okay. Well, here's x, but I need a minus 3. Is that all on the same axis? It will be, right? And it'll show the x and the negative. So the negative 3 and the minus 3, we're going to use those synonymously because we know they're equivalent. And then the x minus 4 on here. Okay. So, and don't worry, we're going to do more multiplying and dividing next week. I just want you to see some of the stuff that comes out here. Okay. Notice that whenever I need to fill in, now I need to fill in my rectangles here. I'm actually going to have something in every quadrant now. So up here, what fills that is an x squared. Over here, what fills that is an x times 3, 3x. Over here, this is an x times 4, 4x, right? And over here, that's a 3 times a 4. That's going to be the 12 that we did earlier, right? We know that guy. So it's kind of weird because this just threw me into all 4 quadrants. And I can see 4 little rectangles going on in here. But I can also see overall this all looks like one giant rectangle, right? So I've got 4 little pieces, the x squared, minus 3x, minus 4x, plus 12. So let's see if that works out the same way, that what we think is going to happen here. Okay, so let's actually do the math. It's turning into a long video. I'm going to be done in just a minute, I promise. Okay, so x squared minus 4x minus 3x, negative and a negative is a plus 12, right? Okay. Hey, look at that. That's what we had. Minus 3x minus 4x plus 12. All right. And if you look, you can see how things still, if I shove them together, things are still breaking into all the right places. I haven't messed anything up, right? I still have one giant rectangle there, so I'm happy with it. And then we could go on from there to talk about combining like terms and all of that. In fact, these are negative 4x's and those are negative 3x's, so what do we think about that? Altogether, that's going to be negative 7x's, right? So we know when we do this combining like terms, that's actually what we would get. Good deal. All right, so I feel like this is enough for 1 week. You're going to have plenty of work to do with these. With working on these patterns, these things like that. I had a question for you for your participation grade. Oh, it was, how do you know, how can you, no, I don't want you to have to explain stuff. Okay. Tell me what it means on the Algeblock maths to be doing the operation of subtraction. Okay, I used 2 very particular words when I was doing that operation. So tell me what that means and send me an email. All right. Housekeeping video coming up.